Apple II wire-by-wire build. Video and CPU bring up. I'm Dr. Matt Regan. I initially built a more conventional raster generator, but it uses a lot of chips. In parts 8 and 9, I looked at H-Sync and V-Sync. In part 10, we went through Steve Wozniak's addressing scheme, and in part 11, we did a bring-up. Now this is a more conventional raster generator, so I wanted to try something a bit more clever. In parts 12 and 13, we built and programmed the EPROM raster generator. Part 14 was about the clock and how colour works with NTSC, and in part 15 I went over the clock build. So now the question is, does it work? First I want to see if I can get this build to display Pac-Man, like I did in part 11. This is the load signal on the shift register. It should occur about every microsecond, which it does, and the signal should be low for about 70 nanoseconds, and so that also appears to be correct. I'm going to call this good. Now let's look at our dot clock on the shift register. This should be about 7 MHz, which gives it a period of 140 nanoseconds, and that looks right too. This is our character clock, and it looks the same as before, but now I'm going to short the wide character input, and yes, I probably shouldn't be using these tweezers to do so, but when I do, the signal becomes more symmetric, which is what we'd expect. I'll show you that again. I want to be able to turn the clock on and off with our Arduino, so I'm going to wire the output enabled signal directly up to one of the control lines. It's currently wired to ground, so I'll disconnect that. I've connected up our crystal oscillator to the main clock through a divider, and I've put it under the control of the Arduino. So now I can either directly clock the circuit from the Arduino, or clock it from the crystal. Now I need to change our Arduino code to reflect this. I should change these magic numbers into actual more meaningful symbols. I'll do that later, but what could go wrong? Now I want to connect the main clock up to the crystal oscillator. First I'm going to make the clock signal from the Arduino an input, then by writing 0 into port J, it turns on the output enable on the clock circuit. After that I don't really need the Arduino, so I'll just leave loop empty. Our raster generator should be under main clock control, and I should be able to see our combined sync signal and our active signal. So this is looking at combined sync. That looks pretty good. It looks about 64 microseconds wide, and occasionally I can see this low section which represents our V-sync. We can see our V-sync signal superimposed on our H-sync signal a bit better at this sweep rate. Specifically, look for these little transient signals at the bottom of our trace. Pin 14 on the 138 is our active bar signal. That looks pretty good too. I'm starting to get quietly optimistic. Let's get on to the next part of the build and see if it actually works. If you remember back to video 11, I created this solid pattern on the screen just using the sync and the active signal. I'm going to try and recreate that here. Our active signal is active low, but I'm going to use it as the video signal, so I want it to be active high. So I'm going to need this inverter to do that. And I'm going to connect output 7 up as our C-sync bar signal. Now I'll connect up the wires to do this. I'm going to use the emitter follower circuit that was designed for our composite signal generator. This is identical to the circuit that I used in part 11, so I know it works. I'm going to stick with it. There are 3 main inputs. From the top, there's color burst, then active, then combined sync. For now, I'm just going to connect the colour burst to ground, but eventually I'm going to make a circuit like the one was used in the Apple II. Just a couple more wires, and I'll be ready for the first real-time test of this EPROM raster generator. Now that that's done, I'm going to power up the circuit and hook it up to the display. And there we have it, our solid rectangle. This tells us that the raster generator is sweeping through memory and generating signals that the monitor can lock onto. Let's see if we can generate an actual display. I'm going to AND the output of our shift register with our active signal and feed this into our analog composite signal generator. Well, that's disappointing. I'm just getting this random pattern. But the signal is stable, which is good. At first guess, I think I'm just pointing at the wrong part of memory, the part that doesn't contain Pac-Man. I'll start by having a look at some of these signals. The EPROM has power, and the data lines are flipping. D2 on the EPROM is next to ground, and I accidentally shorted it and got this pattern. Every 7th pixel's missing, so this tells me the shift register's working. The remaining data pins appear to be flipping, so that's good. The chip enable on the EPROM's high. Now that's at least part of the problem. Let's have a look at the chip select on the static RAM. That's low, so I think I'm displaying the contents of uninitialized memory. There we go, I've been bitten by my magic numbers. The EPROM output enabler is bit 0. If I'd used more sensible labels, this probably wouldn't have happened. I fixed it, and then at the end of download, this happened. Voila, Pac-Man. Despite having finally caught COVID-19, I'm feeling pretty good about how things are going. In my unplanned leave, I finally got some time to get this system working as a whole. I want the bus enable signal to be controlled by both the clock and the Arduino. But the way it's set up, there could be contention. So I'm going to AND the Arduino signal with the clock and feed that directly into the BE pin on the microprocessor. Unfortunately, I've run out of AND gates, so I'm going to have to add another chip to the design. I've got some space down here, so I think I'll add it here. Now I've copied the ROM into the RAM, and I'm going to try and display the image that's coming out of the RAM. And I got this. Here, let me play it again. After some poking around, I found out that while this flip-flop is meant to be hooked up to clock, I'd actually connected it to clock bar, so I need to correct that. I also found out that I filmed this segment through a large clump of hair. Fortunately, that won't affect the performance of the circuit. Now let's try and run it again. Well, that still doesn't work. Now, it's important not to panic when something doesn't work. In fact, it should be your expectation that it doesn't work. What you want to try and do is glean as much information as possible from what you see going on. Here, the image itself is stable, which means it's probably the data in the memory itself that's corrupt. The CPU does appear to have written to the memory. We can see this character 1 under both high score and under player. It's just written in the wrong spot. So I think the conclusion we can draw is the memory either starts corrupt or gets corrupted as the program runs. So this derives the first test I want to do. I need to inspect the memory before I start the CPU, and I'm going to do that by keeping bus enable low. This will deny the CPU any access to the memory. So now I'm looking at the image in RAM before the CPU's had any access to it, and it looks good. So I think the CPU itself is corrupting the data in the memory. I know from part 7 that the CPU actually does run the code from memory properly, but that happens when I'm clocking the CPU from the Arduino, without the video circuit, and bus enable's kept high the whole time. The next test I want to do is clock the entire system from the Arduino, but this time, instead of snooping on the CPU memory accesses, I'm going to see what gets scanned out when clock's low. This is essentially what I did in part 13 to check that the raster generator was working. Except this time, both the CPU and the raster generator will take turns accessing the memory. And lo and behold, I'm getting corrupt data. And remember, I've written the code so that it clears the screen whenever the location 2000's hit. This gives me a better idea of what's being sent to the display. But I can see that the corrupt data is permanent, that is, it's consistent between the frames. That kind of points towards a write problem. The data is being written to the wrong location. Now that could be because there's corruption on the address bus or the data bus, or it could be that there's a problem with my read-write bar signal. Let's look at the read-write bar signal in a bit more detail. When bus enable's high, the 6502 will control this line and it'll drive the signal, but when bus enable's low, read-write should go high because of this 10K pull-up resistor. But the choice of 10K was a little bit arbitrary, and it was really meant for low-speed testing. I know that every wire on a board and every pin on a chip will have some parasitic capacitance, so let's see if we can guesstimate what this might be. The datasheet says the read-write pin itself might have 5 picofarads of capacitance. The datasheet for the 374 suggests that an output load capacitance of 15 picofarads is more typical. The other thing I want to know is what voltage is considered to be high on the inputs of the SRAM. It looks like the input needs to be 2.2 volts before the SRAM will really consider it to be a high input signal. Now that I've done all that, I can go to this DigiKey website and figure out what the curve's going to look like. I can approximate the circuit with this voltage source, switch, resistor, and capacitor. So for a 5 volt signal with 15 picofarads of capacitance and a load resistor of 10k ohms, the time constant is 150 nanoseconds. So what does this mean for our read-write signal? Well, if we use a threshold of 2.2 volts, and the RC time constant is 150 nanoseconds, then it probably takes 80 to 90 nanoseconds for the SRAM to recognize it as a logical 1, but the SRAM itself has an access time of 70 nanoseconds. So here's what I think's going on. The clock and bus enable signal should have sharp edges because it's being driven by transistors in both directions, and by that I mean that the signal is never allowed to float. It's either driven high or it's driven low. These transistors can deliver a lot of current, so the edges are very sharp. Similarly, the address bus is always driven, so its edges should be sharp as well. CPU has access, then video, then CPU again. But when bus enable's low, the read-write signal is essentially disconnected from the chip, and it's just pulled high by this weak 10k resistor. In this example, when clock's high initially, there's a desired write being performed, but because it takes a while for the signal to reach 2.2 volts, we're getting this undesired write at the start of the video cycle, but the signal's wide enough that it actually performs a write into the static RAM. Now fortunately there's a pretty easy way to test this hypothesis. I just need a stronger pull-up resistor. I've put this 1.5k resistor in parallel with the 10k resistor, so these resistors in parallel should give me a resistance of 1.3k. Let me plug 1.3k back into my RC time calculator. So now the RC constant's 20 nanoseconds, which means my unwanted write signal is probably going to be 10 or 12 nanoseconds. So let's see how that works. That seems to have fixed the problem when I clock it with the Arduino. Now for the big test. Yes, it works. This is a pretty big milestone. The CPU's playing Pac-Man in real time, and it's being displayed on our EPROM-based raster generator. Right now, the Arduino is actually just sitting there doing nothing. I've got a bit more work to do. I need to center the image and move the active signal to cover this garbage on the left of the screen. I need to get text mode and to get color to work. I'm also keen to get the keyboard and the disk drive interface to work as well. I showed this example of the pull-up resistor causing a problem, mainly because it's something you might run into yourself, but I think I'm going to use a gate to solve the problem long term rather than a pull-up resistor. For now, I'm just going to revel in the moment. That's it for this video, and please remember to like, share and subscribe. It really helps the channel.